Well, hello and welcome to Flame Testing and Atomic Spectra, a brief activity that ties in with the Bohr model of the atom. Today we're going to talk about the light that is produced by atoms when we heat them up or excite those atoms. To excite an atom means to add energy to it, as we talked about in class. And then when those atoms absorb energy, it goes into the speed of the electrons. So the electrons move faster. Eventually, they slow back down because of the forces that are acting on them from the nucleus, the positive protons that are attracting them. And so when they slow back down, they have to release their excess energy. When they release their excess energy, it's in the form of light, some of which is visible, but not all. We can look at the visible light and we can actually see the different wavelengths and colors that are being produced. And in doing that, we can identify what's going on with the electrons. As it turns out, every atom produces a unique signature of light wavelengths, a unique combination of colors, so to speak, of light. Atoms also produce infrared and ultraviolet light that we won't be able to see, but nonetheless, we'll be able to take a look at these. Now, follow along with the handout in your packet. It's the first page after the schedule, and we're going to go in the order of those elements. The first up is lithium. Lithium is in group 1 on the periodic table. And then when I put this in the flame, you're going to see the color of the flame change. So record your observations. And we can't do that for too long because eventually the metal will heat up, and as you may know, many metals will glow when they heat up, and that will contaminate the colors that we see. I'll do that a second time. Feel free to pause and rewind if you need more time. Now we're going to employ another tool to help us see these colors, and that's known as a diffraction grating. A diffraction grating separates the colors of light into their individual wavelengths so that you can see them. It's a lot like what a prism does to sunlight. The prism separates the sunlight into the rainbow. You see all of the different colors. That's a continuous spectrum because there are no gaps in it. What we're going to see are separate individual colors that are being produced. Now with flame testing, which is what we do with metal elements, this isn't as precise. When we get to nonmetals a little bit later on, we'll be able to see much more accurate breakdowns of the different colors or the different wavelengths of light that are being produced. So I'm going to put the diffraction grating over the camera lens. You can see right away that it creates a sort of rainbow effect. You can see the blue and green colors of the flame that we're seeing there separated. Notice that they're still kind of blurry. Okay, they're not like very sharp. You can also see just a tiny bit of red maybe off in one edge. Okay, those are the colors of the flame, plus probably a little bit of light contamination that comes from the sunlight that's sneaking into the room through the closed blinds, or from the hallway light that's coming in from the window above the door that I can't close. So now let's look at lithium again with the diffraction grating over it. And what we saw as orange is now revealed to be what? Record your observations with the diffraction grating there. And again, I'll do each of these twice, but feel free to pause and rewind if you need to add more observations. Next up is sodium. We're going one space down on the periodic table, but still in group 1. Elements in group 1 are supposed to have similar properties, particularly similar chemical properties. Although this is not a chemical property, we can see whether sodium is going to be similar to lithium. Here's sodium first with just the eyeball. And now sodium with the diffraction grating over the lens. See if you can tell the difference between sodium and lithium. and record your observations. The third element is potassium. We're continuing to be in group 1, moving down yet one more box here. And let's look at the color of potassium. Different. Yet, our eyes are not very good at seeing combinations of colors. And so we may need the diffraction grating to really show us what the difference is, or how much difference there is between this and the two previous that we saw. Now potassium with the diffraction grating in place. And again, as soon as the metal starts glowing, I have to get out of the flame, or else the color of the glowing metal will contaminate the color from the element that rapidly evaporates. I've got small little solutions of these elements here. One more time for potassium. Next, we're going to move over to group 2, the alkaline earth metals, and we're going to start with magnesium, which is one of my favorites. It's very bright. Hopefully that won't be a big issue through the screen, but just be prepared for that. It also takes a second to get going because this one's in solid form. It doesn't need to be in a solution or in powder form to do this like some of the other elements do. So magnesium. Cool. You can see why I like it. And now magnesium with the diffraction grating. Unfortunately, it goes away quickly, so don't be afraid to go back and rewind. You really don't catch the colors of the magnesium with the diffraction grating until the very end as it starts to fade out. Continuing in group 2, below magnesium is calcium. Again, it goes away quickly. I'll do that a second time before the diffraction grating. It's interesting to note that calcium has some similarities to some of the group 1 elements that we saw. In particular, it's right next door to potassium and has some similarities there, but mostly to sodium and lithium that we saw earlier. Let's take a look at calcium under the diffraction grating and see if those similarities hold up. One more time. We're going to continue our way down group 2 and move to strontium as our next element, and then barium. And then after that, we're going to take one of the transition metals just to show you some of the differences that can happen when you get into the middle of the periodic table. This is strontium. Goes away quickly. Let's see if I can get a better sample of it. Yes. Did. There we go. That's strontium just by the eye. And now strontium with the diffraction grating. You should be making note of different colors you see when they're separated by the diffraction grating. Some can be surprising. And that's it for strontium. Our final element from the alkaline earth metals in group 2 is barium. This is barium. That one didn't give us a whole lot of color. Let's see if I can do better. Only a little flash there. Let's do that again. The final alkaline earth metal from group 2 for this demonstration will be barium. That orange at the end comes from the metal loop, so you have to catch the color early. Barium doesn't like to stick around for too long. Try again. And now let's try barium with the diffraction grating. Again, be ready because it goes away fairly quickly. Well, that one stayed around a little bit longer, so that's good. One more time for barium. The last element for our flame testing portion of this activity is from the transition metals. Transition metals can be much more colorful than the other elements on the periodic table, but unfortunately a lot of them are toxic when burned. One that isn't too bad is copper, so we're going to use copper here as a demonstration, and then later on we'll have to examine a different way to find the colorful nature of the transition metals. This is copper. That one evolves over time, kind of changes colors as you go on. Let's do that again. It does stick around for a long time as well. Now it's worth noting that several cultures have learned about this colorful nature of certain elements when you apply heat to them. And in particular, Chinese culture used this to create the world's first fireworks. You can see how heating up these elements in fireworks could be very effective at creating colorful explosions. Let's look at copper again with the diffraction grating in place. And one more time for copper. In particular, that bright flash near the end is very interesting. Rewind and look at it again if you didn't catch it. All right, we're back for the second part of this activity, which is using what are called spectrum tubes or spectrum lamps. This is what we do for nonmetals as opposed to the flame testing for metals, because a lot of nonmetals are actually flammable, so if you put them in fire, they tend to either explode or be consumed. Instead, we use electricity to heat up or excite the atoms, and the same thing happens. But this is more precise than flame testing, so you're going to see much clearer definition on the specific colors. And remember, these colors, or wavelengths of light that are being produced, correspond to specific energy changes for electrons inside the atom. We'll start with hydrogen, and in all cases we'll do regular eyes first and then diffraction grating, just as we always have done. So this is hydrogen when it's excited by electricity, just with regular eyes, nothing else going on. And now we'll look at hydrogen with a diffraction grating. And when we do, you can see in the spectrums that are produced, notice that the same spectrum is produced over and over again. There are three very bright lines that stand out clearly. Red, a light blue, and then purple. The purple one tends to be blurrier and wider than the others, but it's there. So there's three very bright lines that stand out. Make sure you record that on your handout, because we'll come back to those lines a little bit later on. All right, so thinking of those three bright lines that we saw on the hydrogen spectrum, each of those corresponds to a change in speed of the one electron that's in the hydrogen atom. And it's that information that started Bohr on the process of trying to determine his model for the atom, which, as we're going to learn going forward, has a big flaw in it, and we're going to need to correct that. But the energy of the electrons is reflected in the wavelength of light. And so by measuring the wavelength of those three bright lines, we can determine the different speeds at which the electron could be traveling, or the different energy levels for the electron. Now, it turns out that there's also a lot of other light going on. There's infrared and ultraviolet light being produced by hydrogen, and when you measure all that, you get 21 wavelengths of light being produced, which represent 7 different energy levels, changes between 7 different energy levels, which is part of the Bohr model, and something that we still hold true today. That's not the bad part of the Bohr model. Next up on our list is helium. Helium was actually discovered this way. It was discovered in the sun by analyzing the spectrum of light that comes out of it. This is what helium looks like when lit up. Now let's try it with the diffraction grating in place. All right, so you can see a little bit more going on there. Let's see if we can get some separation from those. Notice different bright lines appearing. There is a red one, but it's very dull. To my eyes, it looks almost brown. Then there's a bright yellow, and then green and blue side by side to each other. There's actually more in there, but this diffraction grating just isn't going to be sharp enough for us to distinguish. But in between the green and the blue, there's actually 2 other lines in there. There's 6 visible lines in the helium spectrum, which is a lot different from hydrogen's 3. Now, Bohr's initial theory was that the same 3 wavelengths of hydrogen would be present in helium, and then the second electron in helium would just add more lines. But as we can see, and as Bohr found out very quickly, that is not true. The same 3 lines from hydrogen are not present in helium. And so what he had not anticipated is that the second electron changes the behavior of the first electron. And so the presence of 2 electrons means that each of them behaves differently than the 1 electron that was in hydrogen. So in other words, Bohr's model is too simple. It does not account for the complexity that's going on inside the atom, and we're going to need to upgrade it. It has another fatal flaw that we'll discuss next week as well. So let's talk very quickly about this complexity, and we'll use nitrogen as our next example. This is nitrogen, just plain eyes. Note your observations. And now let's try it again with the diffraction grating in place. And you can see very quickly that there is a lot more going on here in nitrogen than there was in any of the previous examples. In fact, it's awfully hard to even count the number of lines. You get the impression that there's many lines with small gaps in between them. Now that might be accounted for by the fact that nitrogen has 7 electrons instead of the 1 in hydrogen or the 2 in helium. Nonetheless, Bohr's model fails to account for this complexity, and because of that, we're going to have to use a different model. But Bohr's model was useful for a couple of things, in particular for determining the number of energy levels, which is something that still holds true. So as we saw with nitrogen, there's a lot more going on in the atom than Bohr could account for. And we're going to update Bohr's model and bring us into the modern understanding very soon. In order to do that, you'll have to learn a little bit more about the behavior of electrons, and that'll be next week's topic. Let's just finish this out, though, for the sake of it being interesting and fun to look at these, and we'll look at a wide range of elements right now. A lot of them noble gases, and like helium, noble gas, we're going to move on to the most famous element for this particular property. As you might guess, this is neon. As you can see, neon is a real powerhouse, super bright, and as you might guess, there's a lot of reds and oranges in neon's spectrum. But what a lot of people wouldn't guess when you separate them out is that green line that's hiding in there. This is a perfect example of how our eyes are not good at combinations of colors. We do not do a good job with our naked eye of separating combinations of colors. And so we don't see that green with the naked eye at all. There's no indication of it, just the oranges and reds that we would expect. However, the diffraction grating reveals it. And as we'll see going forward, green is the one that likes to hide a lot amidst other colors. This is neon. Moving down the noble gases, we have argon next. Argon doesn't put out quite as much power in the visible spectrum. Some of that is just a property of the element, and some of it could reflect that there's a lot going on that's not visible, like infrared or ultraviolet light, that we can't observe this way. Here's the diffraction grating. Now notice, in this particular case, a lot of reds and yellows, and again, a little bit of green hiding. I guess more of a greenish yellow than a true yellow. You see the blue and purple that you would expect, but the red and green is not something that you would expect from the naked eye. So again, those colors tend to hide sometimes. Notice the difference in power, which might have to do with how many electrons are making that change, but could also be a characteristic of the atom. I couldn't find the krypton tube, so we're skipping over krypton and we're going straight to xenon. Leave the space for krypton blank, and I'm going to fill in a bonus sample a little bit later on in that space. Next is xenon. Xenon has a characteristic lighter bluish color without the diffraction grating. With it, you can see not a lot of difference actually. And xenon is one that doesn't hide a lot of colors. There's a little bit of red in there. Notice the big gap between the blue and the reds. Those are spaces where wavelengths are not being produced. It means electrons are not producing those energies of light. All of these correspond to specific changes that are allowed to happen inside the atom, which means that the electrons in these atoms are heavily restricted. They are not just allowed to move around at any old speed they want to, but rather there are forces acting on them that keep them at certain speeds, which we can then find out by evaluating these wavelengths and doing some math. Luckily, someone else did the math for you. You don't have to do it on your own. Next up is mercury. Now, if you've ever had what's known as a CFL, or compact fluorescent light bulb in your house, those are the ones that have the spiral curlicue kind of shape to them, you may have looked on the container and seen that it talks about the presence of mercury vapor. Mercury has been used in fluorescent lights for a very long time, but it is toxic to breathe, and so when you dispose of those, you have to dispose of them carefully, or if you break one inside, you're supposed to ventilate. Mercury is very effective in fluorescent lights and produces something close to white light, but not quite. You can see it has a slightly blue tint to its white light. And although mercury has a large number of protons and electrons, it actually has a remarkably simple visible light spectrum. Let's get that to focus. There we go. Yeah, it's much better. As you can see, there are three very sharp and distinct lines in the spectrum. Make sure you're not getting overwhelmed by all the repetitions of the same spectrum. Just focus in on one. You can see the bluish purple, a yellow, and then right beside that is kind of an orangish color there. It's not as bright as the others. So mercury has a very simple spectrum. If it had more of a red in there, it would be very, very close to white light. In reality, to get an approximation of white light, we have to put more than one element in the bulbs. Or we have to use something entirely different, like a light-emitting diode, or LED, which is a combination of red, green, and blue light sources that blend together to white. Even then, light bulbs are not perfectly white. Only sunlight is true white. The light bulbs often are tuned to be a little yellowish, which is considered softer and warmer, or a little bluish, which is considered harsher but sharper and clearer for your lighting. And you can buy light bulbs accordingly. Next up is a mixture of different elements. This is air, which, as I'm sure you know, is predominantly nitrogen, but also a significant portion of oxygen. So it's a combination of those two elements. Now, as we might expect, it mirrors nitrogen quite a lot. But when we look at this, there's a few other lines in there, and if you want to, you can take the time to go back and look at nitrogen, rewind the video, and go back to look at nitrogen. And when you do, you'll see that there's a few more lines that have been included in this spectrum than were present in the nitrogen. And those lines are in the greens and yellows, I believe, and those represent some of the brighter lines for oxygen. Oxygen is notoriously not bright and is very difficult to spot in a spectrum. And if you look in particular at the spectra on the far outside of your screen, you can see that a lot of the lines don't even show. Only a few of the bright ones are in there. We'll come back to that thought in just a minute. Next up is carbon dioxide. So carbon is an element that we cannot get in gas state very easily. So it's not easy to do it on its own, but we can put carbon dioxide, which has carbon and oxygen. That's a gas, and we can put it in a tube, and then in so doing, we can look at the carbon spectrum, and you can see it in there. The bright lines are the carbon atom. If you compare back to the air just a minute ago, you'll notice that these are different. The oxygen is still in there, but the oxygen lines are so dim in comparison to the carbon lines that they're very, very hard to see here. And so a carbon dioxide spectrum effectively becomes a carbon spectrum because of the weakness of the oxygen's signal. Our final sample of the day is water vapor, and so I want to bring you all the way back around. Remember the very first one that we looked at, hydrogen, which had a bright purple, a light blue, kind of aqua, that was very bright as well, and also a red, a bright red. So when we turn on the water vapor, we're going to look for those same three lines in here, because hydrogen will produce those three lines whether it's in a compound or by itself as an element. And so when we put this in front, you can in fact see those three bright lines. Purple closest to the inside, then right next to it is the bright aqua blue, and then to the far outside of the spectrum is the red. Those are from hydrogen. And then notice the two fainter green lines that are in there, which I've referenced before. Those are from the oxygen. And so you can see lines that identify each of the elements. This is actually how in criminal laboratories, such as those represented in TV shows like CSI or NCIS, this is often how they identify unknown materials, is simply by either shining lights on them to get the elements to absorb the light, or by exciting them to get them to produce the light. That one gets dim if I leave it running too long. Well, that's all for our activity. I hope you enjoyed this. More importantly, I hope you're able to make the connection to the information that we had in class about Bohr's model and what's also in your notes. So now would be a really good time for you to go back and go over those Bohr model notes again, remembering that there's always some things that we don't go over in class that you need to cover in the notes. And then tie that into your practice. Complete all the Bohr's model practice by next week, and we will move on to the new model of the atom on Monday.